Hello, I'm Kaustav Chatterjee, and welcome to the demonstration of our CPS project. Our CPS project is numbered 1739206, and in this presentation, we're going to demonstrate the performance of the proposed algorithms concerning anomaly detection and data recovery in the context of wide area monitoring of large power systems. Let us first understand the nature of the data anomalies that we encounter in power systems. These are mostly spurious bad data outliers, missing data samples, or at times it could also be malicious injections from cyber attacks. In our work, we have proposed a robust PCA or principal component analysis based method for detection of such anomalies and subsequent recovery of the clean data. Our work premises on two major assumptions. First, being that the nature of the anomaly is sparse across the sensors or PMUs, which meaning that you cannot have a good number of sensors corrupted at a given instant of time, or rather all sensors corrupted at a given instant of time. And second, that the true data or the clean data is low rank, and this can be justified from the fact that the data points or the sensors are correlated amongst themselves, and the measurements are actually drawn from the response of a dynamical system. Without much further ado, let's understand or quickly recap what a robust PCA does, and which is illustrated in the figure below. You can see that this is a low-rank matrix completion method using a sparse optimization technique. The method is essentially a vector processing approach, implying that each data point is processed at a particular instant of time. And also we have to consider what are the guarantees of data recovery for, say, S number of data anomalous sensors. It says that if your denseness of the signal set, I mean the entire signal set on which you are working on, if the denseness of that value is below a given number, for us it's 0.56, then we can guarantee that S number of corrupted signals from that set can be recovered. Now the question comes to how do we ensure that the density of a signal set is below 0.56? That if we are able to group the PMUs or the signals coming from those PMUs based on their modal content, then we can, to a good degree of certainty, say that we can attain this denseness value and therefore guarantee recovery. So what we essentially look for is grouping signals having modal observabilities in phase and their magnitudes tightly bounded in a range. And this has to be done for each of the poorly damped modes present in the system. Let's quickly go to our GUI and demonstrate what we are looking into. First, we will see this for IEEE test system and the synthetic data from that test system. We are looking into the New England, New York test system, which is 16 machine 69 bus system, shown in this figure here. But all the buses are numbered between 1 and 69. So we are here looking into the bus voltage magnitudes, phasors from those mentioned buses. Let us first select bus numbers 19, 20, 21, 22, and 24. These are buses in the New England region of the test system. As we load the data, you can see that their modal observabilities and magnitudes are quite close by, and therefore the denseness value is below the number that we have prescribed, and there the green light signifies that we can go ahead with the data recovery process. Now for first checking that, let us corrupt signal 20 between say time instance 4 seconds and say 6 seconds. 2-second data corruption, and the nature of data anomalies, let's do spurious outliers. Let us first corrupt the data. You can see it's a red trace, and then we'll go ahead with recovering the data. Here, the green trace is the true data point, the trace of the true data, and the blue is the recovered data. And you can see that the blue data quite well traces the true data instead of the corrupted data points. Now this can the other side of it can be checked if we just include a voltage from bus 35, which is from the New York part of the test system, and instead of bus number 20, and then if we load the data, pardon me, I have to clear this first. And then if I load the data again, you can see that the denseness value is much closer to 1, implying now that the subspace has indeed sparse vectors and it's difficult to recover it. I will also demonstrate that. Now let's corrupt 35 between the same instance, the same type of corruption. This is what, and let's try to recover it. You can see. So the green trace is the true signal and the blue trace is the recovered signal. And you can see that the blue trace is quite different from the green trace. And in fact, the blue trace is overlapping the red trace, which was my corrupted signal. Now, this shows that you cannot group 35 with all these signals, because also from the figure, you can see that it has a different phase in terms of its observability of the given mode. Hello. Now we are showing you the data recovery performance for an actual field PMU data from New York Power Authority, which we have gathered from the organization. Now, first, these are again the voltage magnitude signals, and let us first corrupt a given set of signals. Let me uncheck this signals here. Quickly, and first let us corrupt signals 7, 4, 11, 13, 22, 16, 17, and 24. So these are 8 signals. We're expecting them to have same modal phases and amplitudes. Yeah, that's what you can see. And look at the, it is not just that the 1 sparse recovery value is 0.3, so it's guaranteed to recover. It's also the 2 sparse recovery is below the 0.56 numbers, where now we can corrupt 2 signals and guarantee recovery. That is shown here. We have corrupted signals 6 and 15. Sorry, we don't have 6 and 15 in the signal set. Let's just change this number here. We say corrupt maybe say 17 and maybe 24. Okay, we do missing data attack between instance 60 and 65. So these are the corrupted data, and let's recover the data. Well, now as you can see, that the green trace is the true data point and the blue trace traces the green for both the signals and not the red trace, implying the success of the data recovery. Now let us do it for another signal. Let us include let us exclude, say, for all these signals, and this was clear the data, and then uncheck this. Let us now have the signals, maybe let's choose 22, 4, 11, 15, 7, 20, 21, and 27. And let us corrupt. So let's load the data. As you can see that there is a difference in their modal observability magnitudes and phases. And for 1 sparse recovery is guaranteed, it is below 0.56, but 2 sparse recovery is not guaranteed. So you cannot guarantee to recover 2 data points. So let's now corrupt maybe 22 and 4. 22, and let us corrupt 4. Same. Now let's try to recover it. As you can see, the recovered data, the blue trace is actually tracing the red data point that we have shown below instead of the green, and therefore the recovery is not guaranteed. It just illustrates the point that we made. So thank you. This was our demonstration.